The idea here is, well, let's just talk about the general idea. If you're selling some item, then you expect that the more you charge for it, the fewer you're going to sell. And if you charge too much, nobody at all is going to buy it. Now, you might just give it away. If you just give it away, well, there's probably a limited number of people who want to buy it. Okay? So you're not going to give away more than what you would get from the number of people who want to buy it. Okay. Now this is an oversimplified model, but you might have a model that goes like this. Let's say that the most items anybody would want would be 50,000. Okay? And let's say that you've determined that for every dollar you increase the price, 20 fewer people are going to want to buy it. Okay, then if P is the price, the number you're going to sell is going to be that 50,000 minus 20 times P. It's going to, and we're going to model this as a linear function. Now, it really, in the real world, isn't a linear function, especially when you get near the maximum price or near the price 0. Okay, it does. The domain of this function would not really run from a price of 0 to a price of $2,500, for example, because if the price is $2,500, 20 times that is 50,000, and that's a price at which you would expect nobody to buy it. Okay? Well, before you get to that price, you probably get to a price where complicated factors start getting involved. Now, you don't have to understand all of that, but just understand that this is a linear model. Q is a linear function of P. Okay, if you graph Q versus P, you have a straight line. When P equals 0, Q is 50,000. So if you do Q on this axis and P on this axis, you have 50,000 here. So I'm going to write 50K and a little arrow, and hopefully you can read that. When P is 0, Q is 50,000, because if you plug in 0 for P, you do get 50,000 for Q. Also, you can set this equal to 0 and easily solve it for P, and you get P equals 2,500. If P is interpreted as a price in dollars, then at the price of $2,500, this model says you sell none. Okay? Then, this is just the first power of P. This is like a y equals mx plus b. Of course, it'd be y equals b plus mx. You know, if your P was an x, then your Q was a y. So this thing has a slope of negative 20. Now, you might not understand every detail of that as I say it. I'm trying to give you the flavor of this. So your Q versus P graph would look like this. Now, by what I've said before, probably when you're close to price 0, you would say that you can't find another color of chalk anywhere. You would say that, okay, well, actually, we're going to eliminate this part of the straight line. That's going to be eliminated from the domain of this model. And we're going to eliminate this part of the straight line, okay? Because that part of the function probably isn't linear, because as you get close to price 0, as you get close to the maximum price on this model, psychology takes over in a way that prevents this thing from being linear. And it probably isn't linear between here and here, but it's probably reasonably close to linear. Now, this is a kind of model you use in business. Sometimes you use nonlinear functions, which are a little harder to analyze. You can't analyze those functions using pre-calculus. You need calculus. But you can analyze these linear functions using pre-calculus and get a lot of insight into what linear functions and quadratic functions could be good for. Okay, well, so Q is how many you sell, P is your price. If P gets all the way up to 2,500, you're not selling any. If P is 0, you're getting rid of 50,000 of them. Okay, let's say you charge $5 for each. Well, if P equals 5, then 20P is 100. So you'd have 50,000 minus 100. You would expect to sell 50,000 minus 100. Now again, P equals 5 is pretty close to the zero price, and the model probably doesn't really apply here, but if it did, you would then conclude that Q is 50,000 minus 20 times 5, or 49,900. And you can verify that calculation. You shouldn't need a calculator to verify it, but if you need one, go ahead. And if you catch me, that's fine. Okay, then what would our revenue be? Well, our revenue is how much money we take in. So if we charge $5, we sell 49,900 of these things. How much money do we take in? Now, this is not our profit, this is our revenue. You know, you've got to subtract the cost of doing business from your revenue in order to get your profit, and we're not going to go there. Okay, we're just talking about revenue right now. Okay, so you sell this many for $5 a piece. Well, obviously then you take in $5 times this many, which I think comes out to $249,950. Uh-oh, probably not. Not $249,500. Okay, because $5 times the 100 that you're short of 50,000 is $500. So again, wrote that down carelessly, so keep an eye on me. I don't really try that hard to keep the little arithmetic errors out of things, okay? Although that thing with the two signs there, that's kind of an unforgivable error. So I don't try that hard to keep little errors out of this, partly because it would be a distraction to me, and partly because I want you to think about these numbers and think about what they mean. Okay, I could write everything out beforehand. I could read it off the paper and copy it from the paper and write it up here, which is what most people my age and most people 20 years younger than me will do. I think we lose a lot if we do that. Of course, we lose something if I keep making mistakes. We've got to balance that. Okay, anyhow, we understand that we have this linear function. For every dollar you raise the price, 20 fewer people will buy it. And up to 50,000 people will take one if you give it away. That gives us our linear function. If P, and we get a graph and we restrict the domain, but, you know, for reasons I've discussed. And then if P equals 5, we conclude that we sell this many. So the amount of money we take in is $5 times this many, which is this much. Okay, well that's just an example. But in general, your revenue, R, as you can see from this example, is going to be the number you sell, Q, times the price. That's what we did here. We multiplied Q, which is 49,900 at this price, by this price. Okay, so we multiply Q by P. Well, Q is 50,000 minus 20P. We multiply that by P, and we get what? Well, 20P times P is 20P squared. Now it's a negative 20P, so we get negative 20P squared. And then it's plus the 50,000P. And of course you can do that multiplication and write out that expression very easily. Now just observe that this is a quadratic in the variable P. Okay, because you have a P squared and a P. You could also have a constant term out here, but we don't have one. So it's like an AX squared plus BX plus C, where C is 0, A is negative 20, B is 50,000. You could set this equal to 0 and solve for P. You could graph it, and that's what we've done up here. Okay. Now we already saw that if P is 0, your revenue is going to be 0, because if you don't charge anything, no matter how many people take, you don't get any money. So when P is 0, this is revenue versus P. When P is 0, your revenue is 0. And if P is 2,500, well, to get 2,500, we set this equal to 0. That means your quantity is 0, which means your point is going to be on the P axis. We know this is a parabola. We know the coefficient of our squared variable is negative, so the parabola is going to be upside down, so the parabola is going to look like this. Now, you don't have to reproduce all of this. We're trying to give you the flavor of this. And we will do this in the actual class with a little more detail and commentary, because we're going to just gloss through this part. What this tells you then is that there's some point, which is the vertex of the parabola, and the p-coordinate of that vertex is a price, and the q-coordinate is a revenue. I'm sorry, the r-coordinate is revenue. And that's the highest revenue you can get. So from your vertex, you know what price to charge to get the highest possible revenue, and you also know what that revenue is. So this is a very neat model. And there's a lot of insight to it. You're multiplying two linear functions, basically, to get a quadratic function. And now you know the properties of a quadratic graph. You can find its zeros, you can find its vertex, and you can interpret those things in terms of what you're modeling.